higher loads. So the higher the load, the bigger the what? The delta, right? So now coming back to the first diagram, where's delta? The yellow surface or the blue surface? Anyone?
Blue.
Yeah, it's the blue surface. Then how come we are calculating the vertical surface? What is going on down here? Okay, right? Right, it's blue. Yeah, absolutely right. So now we are going to draw an element. Okay, we're going to draw an element. So what do I mean? We're going to draw an element. Okay, so now I'm going to put an element down here. Okay, you can see I draw a green box. Yes or no? Okay, so this is what we call an element. Okay, now I draw an element. So I'm going to make our element look bigger. Okay, so I'll come down here. I'm going to make our element look bigger now. Okay, so this is our element, and the element will follow the transformation of this is x and this is y. Okay, so what we calculated, okay, if I were to put the load P, okay, P is down here. Okay, when the P is applied over there, right, we have a shear force coming down on this way. And this shear force is labeled as the shear stress, right? This is the shear stress. The intersecting plane is on the x-axis, and the direction of the shear stress is in the y direction. Okay, so let me elaborate by what I just said. Okay, so this yellow surface, this vertical surface is what of interest. Okay, so this is the first label over here. Is the plane intersecting the x-axis, right? So if I'm going to put this plane onto a transformation, it'll be over here, right? You can see now, and I'm going to highlight in yellow. I'm going to highlight in yellow. Okay, so it intersect the plane intersect the x-axis. The y, okay, the y is the direction. Okay, this over here. The y is the direction of the shear stress. So the direction of the shear stress is in the y direction. That's how you label it. Okay, but because it's shear, right, you will have a counter component. Okay, so if you draw shear on that surface, you're going to have a shear on this surface also. Okay, and this is known as shear. The intersecting this plane over the horizontal plane will intersect the y-axis, and the shear stress is in the x direction. Okay, so shear xy. Okay, so to achieve equilibrium, okay, shear xy must be equal to what? Shear yx, right? So now, if I'm going to put the dimension a down here, right? So this height over here, for example, this is a, right? And we already mentioned at that surface, there's no failure, right? The yellow surface has no failure. This surface is the failure surface. So for this reason, now you can see why failure will occur on the horizontal surface. No doubt our calculated, this surface is what we calculate. Okay, this is our calculated and analyzed surface. Okay, because of equilibrium, shear xy is equal to shear yx. That is the reason. Okay, you have to visualize this. Okay, that's why I have a lot, even seasoned engineers, they will come and ask me, how come the failure is in the different direction? And this is the reason. Okay, any question, anyone?
Makes sense.
Okay, makes sense. Okay, good. I have acknowledgement, makes sense. Okay, now I'm going to draw a 3D element. Okay, regarding the labeling of the, yes.
So please, can you please go back? I just want to
Yes.
finish talking.
Tell me when you're done.
Okay.
So the next thing we're going to do is we're going to draw the element. Okay.
All good, thanks.
We'll look at 3D. Okay, so now I'm going to draw 3D now. Okay, so this is our X, Y, and this is our Z. Okay, so if we were to construct this in 3D space, okay, okay, so this is our 3D space. So I'm going to label the planes. Okay, so for the first one, this over here is the plane intersect x-axis. You can see that, right? Over here, the plane intersect y-axis. And then the third one, the plane intersect z-axis. Okay, you can see that, right? When the plane, when you shift it to transformation, it intersects. Okay, so now when we label, okay, when we label, so this one, right? If I draw this, the shear is going in the y direction, but the plane is in the x. So shear or the intersecting plane is x and y. Okay, and there's always a counter. Okay, so the counter is this one. Shear y, okay, and x. Okay, and let's do another one. Okay, over here. Now the shear stress is in the z direction. Okay, so the plane intersect the x-axis. Z direction is the shear stress, and then the next one, right? So this is the shear, the plane intersect the z-axis, the shear stress in the x direction. And the third one, right? This is the shear intersecting the plane intersect the z-axis is going up in the y. And the last one, this is the shear, the plane intersect the y, and the shear stress is in the z direction. Okay, so 6 separate components. Okay, so the next thing is we are going to look at this formula over here. Okay. Okay, the formula we're going to look at, we're going to focus on shear stress is equal to VQ over IT. Okay. VQ over IT. So this formula is very important. A simple formula, but not easy to analyze. Okay, I'll tell you the first. Okay, it's a simple formula, but not easy to analyze. Okay, so there are 5. Okay, there are 5 major rules to remember. If you don't remember these rules, okay, you will not be able to solve any problems at all. You'll get so confused. Okay, before I start teaching this class, okay, without the rules, I can't do it at all. Okay, I was okay, okay. So let's look at rule number 1. Okay, let's look at rule number 1. Now you don't get this from textbook. Okay, you when you read your textbook, you got no rules at all. Okay, rule number 1. Okay, B and I, the shear force and the second moment of area I are constant okay, are constant regardless okay, regardless on the point of interest. Okay, let me elaborate that. Okay, B and I. Now this rule also apply for the other formula, as in small q is equal to VQ over I for your shear flow. The rules also apply. Okay, the rules also. So what do I mean by that? What do I mean by B and I are constant regardless of point of intersection? Okay, so now let's say that we have a simply supported beam. Okay, now this rotation Z. And then we have, as I said, simply supported. This is point A. A pin and a roller. And then we have our load that is evenly distributed and a point load down here. Okay, so this is our point A. This is our point B. This is our point C. This is our point D. And we have a load down here, which is P. Okay. Now, if we are interested in a certain section, okay, so we are interested in this section over here. Okay, we call this section our small AA section. Okay. So the next thing that we're going to draw is the cross-sectional view. Okay, so cross-sectional view of AA. Okay, so now we're going to view in a cross-sectional view. So I'm going to draw the transformation in a different way now. So we are looking at what we can sometimes call the front view or the end view. Okay, so Y, this is Z, over here is rotation number X. Okay, so now this is a cross-section view. So the cross-section looks like this.